Alright, this video is for Math 116, and this is the second section of 1.9, the second part of section 1.9. And so we're still talking about optimization, and these are the problems that involve geometry and cost. So the idea is we're making a box, and we want to either maximize the volume given a particular cost, or we want to minimize the cost given a particular size for the box. Okay? Alright, so that's the key to doing these problems, okay, is which one are you being asked to optimize and what's the constraint, okay? And I'll talk about those two things as we go through these problems. Alright. A closed box with a square base. Alright, so first off, if we have a square base, that means its length and width are the same, which means that we only need one variable to describe them, and then the height will get another variable. This word closed indicates that the box has a top. Okay? And it's also x by x. Alright? And what are our units here? Feet. Okay. Alright, so that says that the volume of this box is length times width times height, or x times h, x squared h. Alright, what else? Let's see. The cost for the materials is $1 per square foot for the four sides and the bottom. Okay? So four sides and bottom are going to cost $1 per square foot. And then the top is more expensive, $5 per square foot. I think I took this from a problem where they were making a terrarium and you needed like a lamp up here with a glass cover and all this different stuff, so it was more expensive. Alright, so here's the thing. So the cost of this box is based on what you're building it from. Okay, so that's very closely related to the surface area. The surface area for this box is, you've got a top that is x by x, so x squared, and a bottom that is x by x, also x squared. Each side here is x by h, and there's four of them. So those sides are going to be 4xh. Alright, so there's the formula for the surface area. Now the cost here is going to be, let's see, these four sides cost $1 per square foot. Okay. The bottom, let's say this one is the bottom, is $1 per square foot, but the top is $5 per square foot. Okay? So I've taken each piece and multiplied it by the cost for that piece. So our cost function is 5x squared, 1x squared, and then this 4xh stays the same. So our cost is now 6x squared plus 4xh. So this is pretty typical for these problems. We've got a formula for the cost. We've got a formula for the volume. Let's look at what the problem is asking us to do. The dimensions of the box of largest volume. So we're being asked to optimize this volume. Find the largest possible volume for a box that can be constructed for $72. So here's the constraint. Okay, is the cost. Our volume is what we want to graph and optimize. Okay, we're going to get some graph that's doing something like this, and we want that maximum value off the graph, given that we're constraining the cost to be $72. Now here's the trick. Just like in that first part of section 1.9, you know, we had the thing where it was like, we started out, we had like x minus 1 squared plus y minus 5 squared. But then to solve the problem, we had to replace that y with the formula for the parabola. What was it, x squared minus 4 or something like that? Okay? Same thing here. We're going to come in here and we're going to replace that h with whatever we get the h to be equal to in solving this equation and isolating this h right here. Okay? We can't have these two variables in here. We want to get it down to just a function of x. All right. So the one that we're going to use to substitute in or to plug in is the one that we've got the constraint on. All right, so we're going to get the h by itself. So first off, let's move this 6x squared to the other side. 72 minus 6x squared equals 4xh. And then we've got to divide on both sides by 4x. Now, how do you want to represent this? We're going to have x squared and then 72 minus 6x squared over 4x. Well, let's see here. This x will cancel out one of these, so that'll be x times 72 minus 6x squared over 4. And then we can divide these each by 4. 72 divided by 4 should be 18, and then 6 over 4 is 1.5. So here's our volume equation right here. Volume v of x is 18x minus 1.5 x cubed. So there's our formula. If you wanted to graph it like this, you know, x squared times 72 minus 6x squared over 4x. That's fine. You just have to be careful. I'm standing out of the camera. There we go. You just have to be careful about how you enter that. So that's the thing. Like if I simplify this, then that means I can just type this right in and be pretty confident that it's going to be the graph that I want to see. When you get into these more complicated expressions and trying to graph them, then you have to be careful about where you put your parentheses and how everything is getting input into the technology. Okay, so let's go ahead and graph this. And then we'll see what it looks like. Now in graphing these, the standard window generally is not going to give us a view that we want to see. So let's see here. 18x minus 1.5x to the third. So I'll show you what the standard window looks like. Wow, that got pretty darn dark. Why did that happen? But anyway, so there's the graph. You can see the top of the graph is not in the window. All right, so to fix that, what I'm going to do is I'm going to open up my window. So let's see, can I do this without getting the screen so dark? Okay, so there's a look at that. But if we go into window, remember, I can go down here and I can make my Y maximum. Let's make it 30. And then let's see what that graph looks like. There it is, okay? And so there is the peak where we're going to get our maximum volume. So we hit second trace. Maximum is choice number 4. All right, and then remember we have to set a left bound, go up there, set a left bound and hit enter. Now it wants a right bound, arrow past it to the right, hit enter. And no, we don't want to guess, we want the actual maximum, and there it is. X equals 2, Y equals 24. Let's go back to the board and include that information with what we're doing here. All right, so x equals 2. And y equals 24. So remember, the y in this case is the volume, okay? So that's cubic feet. x itself is in feet. Now let's see what questions what are the dimensions of the box of largest volume? Okay, so we just want the dimensions. That means that this is 2, and to find the height, we have to say 24 is 2 squared times h is 6. Okay, so the answer to this question then, what are the dimensions? 2 by 2 by 6 feet. Okay, and that'll give us a box that's 24 cubic feet that we can make for $72. Okay, so you can see these problems are fairly involved and lengthy. I think that's a good thing because this is very typical for math problems once you get past a certain level of mathematics. You'll still run into, and we still see that in our textbook. I said, what I was saying is that you'll still run into, just sort of the practice problems where you have a lot of things like skills problems, okay? But this is something that becomes more and more common the more complicated math you go into, okay? All right, let's look at some of the problems in the problem set and talk about how to solve those. Okay, so over on page 62, let's look at problem 4. So, box with a square base and an open top. Okay, so we've got a square base and no top. Okay, and so that means it's x by h. Our volume will be x squared times h. And what are we doing here? We want to set that volume equal to 32,000 cubic centimeters. So that's our constraint, is that the volume is constrained to be 32,000 cubic centimeters. Find the dimensions of the box that minimizes the amount of material. So remember, the amount of material is the surface area. We haven't gotten into the cost yet, but if you minimize the material, then that generally will minimize the cost. Cost differentials can change that a little bit, but we don't have to worry about that right now. Okay? All right, so our surface area is just the bottom and the 4 sides. Okay? So the bottom is x squared. Each side, right, is x times h, and there's 4 of them, so that's 4xh. Okay, so again, we don't want to graph this with 2 variables, so we're going to substitute in for that h. Here's the constraint piece. We want to get the h by itself. H is 32,000 over x squared. Good, then we come over here and plug it in 32,000 over x squared. And again, you can graph it like this if you want to. Let's see, I'm going to cancel this x with one of these x's, and then also multiply 4 times 32. That'll be 128,000 over x. Okay, so there's a good function for us to graph. I'll go ahead and put it in the calculator, and then we'll take a look at what it looks like on the graph. So x squared plus 128,000 divided by x. And we'll start out in the standard window, and then we'll see what it looks like here. Okay, let's see here. Okay, so there's the standard window. We don't see anything. So let's go into window. Oh, actually, no, going into window is just guess and check. So let's do second graph. That'll show us the table. Let's see. I've got to bring my table back to 0. So let me do that. Okay. So here's our table. All right. So you can see these values. We're looking for the minimum value in this one. You can see they're all in the tens of thousands. So I'm going to go into my y's, and let's see, I'm going to make my y maximum 20,000. Okay, so there's that, and let's hit graph and see what it looks like. Oh, there it is. Okay, so now I need to open up my x's. I need to see over here better. Okay, so let's go back into table, and I just need my x's. Let's go out to 20 on the x's, and then let's see what that graph looks like. No, not quite. Okay, so I'm going to keep opening this up. I'll take the x's out to 50. And I think that's enough to find that minimum value. Let's do this one more time. Take the x's out to 70, and then we'll know for sure. Yeah, there it is. Okay, so there's a good clear look at that function. And now, again, we're going to go second, trace. This one we want the minimum, so we're going to do number 3. And let's see, I think that's a good enough left bound. And then we have to go past the minimum, see when it starts rising up again, then set a right bound. And there's our minimum. So when you see it say something like 39.99999, that's 40. Okay, and our y value is 4,800. Okay, so let's put that information on the board, and then we can answer some questions here. So let's see, our minimum value is coming where x is equal to 40, and what were we graphing? The surface area is equal to, what is that? 4,800 square centimeters. Okay, so this 32,000 was in cubic centimeters, so our surface area is going to be in square centimeters, and the value of x in this case will be 40 centimeters. What did the question ask? Dimensions of the box. Okay, well, we know that x is 40. H is going to be 32,000 divided by 40 squared. And that's going to be 20. Okay? H equals 20. So our dimensions are 40 by 40 by 20. And that'll give us a volume of 32,000, a surface area of 4,800. And that'll minimize that surface area. Okay. Let's look at problem 6. Problem 6, rectangular box with no top. So this is a little bit different, okay? This box is rectangular. That means its length and its width are different. Here's the height. So length, width, and height apparently are all different. And there's no top. All right, the width of the base is 5 feet. Oh, well, now we know what the width is. That's 5 feet. Okay. I'll call this X instead of L. It doesn't matter. You can call it L if you'd like to. I'm just going to use X because it's a more clear letter. All right, let's see here. Material costing 50 cents per square foot. Per square foot is the cost. And the volume is 6 cubic feet. So our volume is our constraint. Okay, and it's going to be equal to 5xh. We want to, what are the dimensions that minimizes the cost, and what is that minimum cost? All right. So let's see here. So for a cost function, right, this is in terms of square footage, so we need to write an expression for the surface area. Our surface area is, the bottom is 5 times x. This side here is 5h. This side over here is also 5h. The front is x times h, and the back is x times h. Okay? All right, so our surface area is 5x plus 10h plus 2xh. And so the cost is the same for all the sides, 50 cents per square foot. And so just multiply that by the surface area. All right, there's our cost function. Now, remember, we need to substitute out for those h's. So, over here, divide on both sides by 5x, and so h is 6 over 5x. All right, let's go ahead and plug that in. 6 over 5x, and 6 over 5x. All right, let's see here. 5 goes into 10 twice, and those x's cancel each other out, so let's see, 0.5. 5x plus 12 over x plus 12 over 5. Okay? So we can multiply this half through or not. That doesn't really make a whole lot of difference. I'll go ahead and do it. 6 over x and then 6 over 5. All right, there's our cost function right there. So let's go ahead and graph that and see what comes out of it. So again, notice what we were being asked to optimize was the cost. That's the equation we're going to substitute into. All right? The constraint came from the volume. That's what we used to make the substitution. All right? And that's the key to doing these problems, is identifying the two equations you're going to be working with. One of them you're going to use to substitute into the other. Okay, let's see here. So our function is 2.5x plus 6 over x plus 6 over 5. Okay. So I'll start out by graphing this in the standard window. Let's see what that looks like. Well, that's not so bad. You can actually see that minimum value right there. Okay, I'll expand our window a little bit. I'll move that y maximum up to 20. And then let's see what that graph looks like. So there it is right there. Yeah, and there's our minimum value. So we go in and we hit second, trace. Minimum is choice number 3. And now it's going to want you to put in a left bound right there. Arrow past it, make a right bound right there. And there's our minimum. X is about 1.55. Y is 8.95. All right, so let's put that information on the board and then see whether or not we've answered the question. Okay, so x equals 1.55. Okay, so that's that measurement right there. And the y, which is our cost, is going to be $8.95. Okay, so that's part of the answer to the question. What's the cost of this box? So there's the cost, and the dimensions are going to be 1.55, and these are in feet, by 5 by what? Let's see here. Our height is going to be, what is this? 6 divided by 5 times 1.55, about 0.77. 0.77, and this is all in feet. Okay. this is, let me draw a little bit better picture of this. You know, the height is not very much. This width, as it turns out, is more like the length. And then there's the width of the box itself is going to be, it's going to be wider than it is tall. So it's going to look something along those lines. Okay. All right. We didn't really need to do that. I just get curious sometimes about what these boxes look like. Okay. Let's see here. Well, I think we'll stop there in this section. And then, like I said, I'll probably do one more video for those last two parts of section 1.9. As always, if you have any questions about this, please let me know.